Welcome to Chapter 11, Part 3, looking more deeply as light as a particle. If you recall from the last video, we said light was both a particle and a wave, and we called that the dual nature of light. In class today, I showed you a demonstration on flame tests without a lot of explanation. This video and Bohr's model explains why we get different colors of lights when we excite electrons. This is Niels Bohr, and Bohr gave us the wonderful planetary model of the atom, which is not true, doesn't exist, doesn't happen, but hey, it still has a very healthy life in most middle school textbooks and even in some high school textbooks. The model is very useful for many reasons. The first one is it allows us to understand energy levels, where n equals 1. This is the first energy level. It can hold 2 electrons. This is our second energy level. It can hold 8 electrons. And this is our third energy level. It holds 18 electrons. Now, if you take a look at a periodic table, you'll notice that in the first row of the periodic table, there are 2 electrons, or 2 atoms. Rather, you have hydrogen and helium, and that adds up to 2. If you look at row 2 and count across, starting with lithium and ending with neon, you end up with 8 electrons. And row 3, well, you probably don't believe me right now. Really, there are 18. And so these energy levels that Bohr came up with was brilliant. But how the electrons behave in these energy levels, yeah, that part he didn't do such a good job with. But the energy levels, yes, spot on. What Bohr noticed was that if you take some energy and shine it at the electron, you put a bunch of energy in, you can actually excite an electron from this second energy level up to the third energy level. But as you know, you can't stay in this high energy state for very long. I mean, really, how long can you stay there? Eventually, that electron is going to fall back. And when it falls back, a discrete, specific light of a specific wavelength is emitted. Okay, so think about our flame tests. Take a look at this animation. As white light, this is white light, and white light contains all of the colors of the spectrum. And as white light goes in, you can see that the electron gets excited from one energy level up to the other. So go ahead and watch it. It goes from the second to the first. That's the first thing I want you to notice. See, light gets hit. Here it comes. The energy comes in. The electron gets excited up to an energy level, and then when it falls back down, look at this. Watch this guy come back down. So here we go. White light comes in. Okay, so do it again. White light comes in. The electron, the wavelength of orange is going to excite it up, and then it's going to drop out that orange color. So whatever light it absorbs, it's going to release. So here you can see it. The orange light is going to be in the absorption spectrum that you'll see over here. There goes the orange. And you can see orange is missing. And when it's emitted, orange comes back out. How does this relate to our flame tests? Another way to look at this is what's called the emission spectra. Basically, you saw the emission spectra in the previous animation, but here we have a gas discharge tube containing hydrogen. So we're applying electricity to this. And the electricity then excites the electrons. So these electrons, they're going from what's called a ground state to an excited state. Whee! They go up, yay! So when this light that hydrogen is putting off gets passed through a prism, we don't get the full rainbow. We get specific, discrete, exact colors right here. You do not get the entire spectrum. How does this relate to our flame test? So a photon comes in, it hits the electron. The electron initially was at the ground state, and then it gets excited up to this excited state where it cannot stay. So when it falls back down to this energy level, whatever photon, whatever wavelength came out, or went in, whatever wavelength went in, that same wavelength is going to come out. Here's another way to look at this. If we have electrons at the ground state and you excite them up to one energy level, you get a wavelength of red. If you excite them up to the third energy level, you end up with a wavelength of green, and to the fourth energy level, a wavelength of blue. Which one of these wavelengths has a higher energy level? Well, if you said blue, you'd be spot on, because the smaller the wavelength, the higher the frequency, and then the higher the energy. So the more energy you put in to excite it way up there, the more energy will be released when it falls back down. So what does that tell you about the energy levels for the specific metals we excited in class today? Remember Rutherford and his wonderful idea that the nucleus was positive and that the electrons were out there somewhere? Well, if he had been correct, and we did an atomic spectrum of hydrogen, we would have ended up with the entire rainbow, because he said the electrons could be anywhere. Electrons anywhere. And we would have gotten this wonderful continuous spectrum that we get whenever we shine white light through a prism. See, this is what he said, like the electrons like on a ramp. It could be anywhere, here, anywhere on the ramp. Bohr showed Rutherford was incorrect because the atomic spectrum is discrete, it's specific. No matter what metal you put in the flames, or what atom for that matter. We could do this with neon. I used metals in the class. But you could use neon or anything, and you get specific spectrums that look just like this. By the way, this is one of the ways we find out what the stars are made out of, is by looking at their emission line spectrum. Think of this like a fingerprint. Everybody is unique. But what this showed, and this is huge, the electrons are found in specific energy levels. Think of it like a staircase. You can stand on this energy level, or this one, or this one, or this one, but you cannot be on a half step. That is not possible. If you are an electron, you can only stand on specific discrete energy levels. And when the energy is excited and falls back down, you get a specific color released, not the full spectrum. And while Bohr's model has some awesome ideas in it, and I really like the concept of the energy levels. I mean, that, like I said before, that was spot on. The energy levels was brilliant. He came up with this planetary model that has some uses for visualization, but essentially the model is wrong. So what's the point of all this? I mean, really, you guys are probably sitting there saying, hey, well, what do I really need to know? Number one, only certain energy levels are allowed. That part is huge. Now, I wrote hydrogen here because Bohr did all of his work with only hydrogen. However, this does apply. Electrons, no matter what atom you are only allowed to be in certain energy levels, and that the energy of the electron is quantized. This word is hugely important. When I say quantize, I mean a chunk of energy. Chunk? Yeah, chunk, there we go. Of energy. Energy comes in these discrete packets. A photon is a discrete packet of energy because energy is quantized, and it cannot be a half like the staircase. Each energy level represents a quanta. Just so you know, make sure you understand that Bohr correctly identified quantized energy levels. And what he got incorrect is that the electrons do not, nope, they don't orbit the nucleus like planets around the sun. This is going to be very important later in this chapter. But take a look at the periodic table. The first energy level, and I said this earlier, contains 2 atoms. And those 2 atoms you could think of as addresses for the electrons. And in the first energy level, you can have, 2 electrons. And there are 2 elements. Easy to count. In the second energy level, there's 8. 1, 2, 3, 4, 5, 6, 7, 8. So the second energy level can hold 8. Sorry, that should have been a biggie. Second energy level can hold 8 electrons. The third energy level is kind of strange. For reasons that you don't want to know today, the third energy level kind of drops here. This is 3. And then it goes back up here to 3. I know that's strange. But count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. And yes, the third energy level does hold 18 electrons. And if you recall, our modern periodic table was put together by Dmitri Mendeleev way before any of these experiments were done. I think it's awesome. So what we're going to do next is we're going to take a look at the electron as a wave.